Hello, for our presentation today, we're going to be talking about thermal remediation methods, which is groundwater treatment through heating methods. For our presentation, we're going to talk about three different types of thermal remediation treatments. One being conductive heating, the second being enhanced resistivity heating, and third being steam enhanced extraction. All very similar setups, but obviously different ways of heating up the groundwater. The first thermal remediation technique that we're going to go over today is thermal conductive heating, which is the application of conductive heating to the subsurface. We use conductive heating and a vacuum to remediate soils contaminated with a large variety of organic compounds. In order to heat up the ground, we use thermal wells, which are wells that are electrically powered to produce heat. These wells are normally at a temperature of 14 to 1500 degrees Fahrenheit. The heat flows through these wells and heats up the groundwater. We have two common types of technology that we use to heat up this groundwater. One being a vertical thermal well, or the second one being a horizontal thermal well, which is also known as a thermal blanket. But we're not going to go into detail about thermal blankets because that is above ground technology. But as these technology heats up the groundwater and the ground surface, volatile organic compounds are either vaporized or destroyed by different types of mechanisms like evaporation, steam distillation, boiling, oxidation, or pyrolysis. This causes the water and contamination to become steam, and once they become steam, the heater vacuum in between the wells are sucked up into the vacuum and transported to the treatment center, where we clean up the water and clean out the contamination from the water and then put it back into the groundwater after completion. For this type of thermal remediation, we set up the thermal wells in a triangle shape and then place these vacuums in the middle of them. So therefore a large pattern of them causes this to become more of a hexagon shape. The next type of thermal remediation technology that we're going to talk about is electrical resistivity heating, which is technology that involves passing electrical current through soil, resulting in an increased subsurface temperature, usually to the boiling point of water. The setup between conductive heating and electrical resistivity heating are the same, where they have the wells and then the heater vacuum in the middle. But the only difference is, instead of thermal wells, we use electrodes, which in the subsurface causes an electrical potential difference, which allows an electrical current to flow between the electrodes. And since electricity can only pass through conductive material, the current will take a path through the conductive material, causing that to heat up through resistivity, which in turn causes the surrounding area, the non-conductive area, to also heat up, which allows for the groundwater and the contaminants to boil to a point where they're vapor, and then that allows the heater vacuum to suck up that steam, which we can send towards the treatment facilities. And then a common misconception with resistivity heating is that the electrodes heat the groundwater itself. A common misconception is that the electrodes themselves heat up the groundwater, but we need to remember that it's through resistivity and not the electrodes. Then lastly, we'll talk about steam enhanced extraction, which has its background in the petroleum industry, where we used it to recover crude oils from reservoirs. There's two modes of steam injections, one being steam soak, which is involving the steam to soak and sit into the area, while steam drive is used to push the crude oil out of the reservoir. But the main difference between petroleum industry and environmental industry is that the petroleum industry has larger depths to go down towards, and the environmental does not go down as far. They're more shallow depths. Therefore, we use the steam in a slightly different way than the petroleum industry does. The steam temperatures used in petroleum industry are normally a lot higher than the environmental ones, just because of the depth at which they have to go. In environmental, we use steam to create a pressure gradient, and we end up recovering more fluid to the setup with. Steam enhanced extraction is the same as the other two, but instead of using thermal conductive wells and electrodes, we use pipes that inject steam, and then we put a heater vacuum in the middle in the same exact way set up. And then once we inject the steam, we do a pressure gradient, which pushes some more fluid out, but we still get hot enough temperatures where vapor is created from the groundwater and the contaminants, which is also then sucked up into the heater vacuum and taken to an above ground treatment facility.
In this section, I would like to talk about the physical characteristic of the pollutant we are trying to remove, as well as the pros and cons of using our thermal remediation methods, to talk about the degree of effectiveness of each. To start with the definition of VOC, VOC is short of volatile organic compounds, which is collection of many kinds of organic chemicals that have a high vapor pressure. They can be either man-made or natural, but today we focus on our attention on PCB. PCB were widely manufactured in the last century, until 1979, when people recognized its health and environmental impact and banned its use. At the right side of the PowerPoint is its structure makeup. Because it is flame retardant and insulated well, it was used in cable insulation or cooling agents. Although it's illegal now, it still leaks from unchecked old machines, and previous releases still exist in wastewater. It accumulates in the soil and aquatic delta with seasonal radiation cycle, also posing threat to human health. Therefore, we choose to focus on this chemical. Let me go into pertinence of each technology in treating PCB. Thermal conduction heating, which I will refer to as TCH, was originally developed to address PCB contamination. It specializes in removing semi-volatile organic compounds and has a higher operating temperature that can reach 800 degrees. Therefore, it is good at treating compounds with higher boiling points or projects with a more stringent clean-up goal. Electrical resistance heating is very similar to TCH in terms of removing pollutants, but at a limited temperature, since it relies on the resistance of media. it is used mostly treated chlorinated organic compounds, but it is limited to reaching the boiling point of the water. It can be used together with TCH in lower permeability areas, and they are both unhelpful when there is groundwater, since it will cool the temperature down. Steam enhanced extraction has multiple benefits, including a thorough treatment range, deep range, and less environmental burden. It also requires less investment because it does not require the labor to drill and bury the electrodes like the previous two technologies. However, it is more specialized in removing wood treater contaminations. Based on the observation above, we conclude that TCH has the best performance in sites put with PCB, although with the limitation that the area is rather small, shallow, has low permeability, and has no flow-in groundwater.
Field implementation. The first one we will look at is conductive heating, also known as TCH. This technique uses thermal conduction, which is a process of heat flowing from the hot end of a solid object like an iron rod to the cold end. In soil or rock, heat flows from the heater wells out into the formation by grain-to-grain contact in soil and across solid objects such as rocks. The fluids such as water, air, and end apples are in contact with the solids that also heat up at the same time. The heat moves out radially from each thermal well until the heat fronts overlap. TCH installation consists of installing a series of patented electrically powered heaters and vapor extraction points in situ to heat contaminated soil to target treatment temperatures. Treatment temperatures are typically 100 degrees Celsius for volatile contaminants and between 150 degrees Celsius and 325 degrees Celsius for semi-volatile contaminants. TCH produces uniform heat transfer through thermal conduction and convection in the bulk of the soil volume. This allows the achievement of very high contaminant removal efficiency with a nearly 100% sweep efficiency, leaving no area untreated. TCH can be applied at low, moderate, and higher temperature levels to accomplish the remediation of a wide variety of contaminants both above and below the water table. It is the only major in situ thermal remediation technology capable of achieving target treatment temperatures above the boiling point of water and is effective at virtually any depth in almost any media. Also, it works in tight soils, clay layers, and soils with wide heterogeneity in permeability or moisture content that are impacted by a broad range of volatile and semi-volatile contaminants such as D-naples, L-naples, tar, PCBs, pesticides, PAHs, explosive residue, mercury, dioxins, chlorinated solvents, and finally, heavy hydrocarbons. The TCH technology can be utilized to heat in situ soils along with stockpiled soils and sediments. The design of the treatment system for in situ soils, ISTD, typically includes vertically installed heaters, which is shown on the left, whereas the design of the treatment system for the stockpile soils, in-pile thermal desorption, or IPTD, typically incorporates horizontally installed heaters, which is shown on the right. Examples of the elements of each system are shown in these two diagrams. Lastly, TCH technology can operate inside, beneath, and near buildings and or infrastructure, and this capability has been field proven at numerous projects present today. Electrical resistivity heating, also known as ERH. This is a technique that has been widely applied and proven effective for free product recovery and enhanced vapor extraction at sites with volatile contaminants such as VOCs, CVOCs, and NAPOs, and is applied at low and moderate temperatures. ERH uses electric current that is passed through the soil, and the resistance it encounters causes both the soil and fluids to heat up. The current then flows from one electrode to another, primarily through the soil water. Once the water boils off, electrical conductivity becomes negligible and heating ceases. Thus, water is added at each electrode to keep them from drying out. The heat up with ERH is limited to the boiling point of water only. Electrodes are installed in wells throughout the contaminated soil and groundwater volume. The electrode array is connected to a power delivery system unit that uses standard, readily available three-phase power from the grid. The process begins by passing current between electrodes, causing the soil temperature to rise. This increased temperature results in the volatilization of contaminant compounds into the vapor phase for removal with vapor extraction techniques. Comprehensive computer controls are used to regulate and optimize the thermal response of the target formation. ERH has many advantages, with the first one being that it has superior energy delivery and heat transfer that is achieved through custom-built electrodes that provide higher output and improved control. Also, it is more effective at energy delivery and subsurface heating that is provided by real-time computerized power controls for each electrode separately. Convective energy delivery is available in permeable settings, making it possible to generate and inject steam for additional heating and contaminant flushing. Lastly, safety and process transparency are enhanced for both the project team and clients with real-time digital at the source temperature and monitoring. The electrodes are typically consisted of graphite, steel, and or electrically conductive material within a borehole. Also, arrays of electrodes are installed in the TTZ. There are multiple stacked electrodes that can be constructed in a single boring. This allows differentiation in the vertical or thick heating of the target treatment zone. Electrical power is delivered to the electrode array by power controllers. Lastly, isolation transformers are used to ensure that the current applied in situ flows only between the installed electrodes themselves. Steam enhanced extraction, also known as SEE. This is a technique that uses steam for subsurface heating, and fascinatingly enough, it will typically be generated on site through the combustion of fuel or gas, which is pretty neat since there isn't a need for outsourcing when it can be produced in-house, making it economically friendly as well as more efficient in the process, which most industries use today. It also requires the use of injection wells that are constructed with special equipment that can both control and monitor the pressure along with the flow of the steam that is being injected into the subsurface itself. Most importantly, at active industrial facilities, this technique is applied by using excess generation capacity of pre-existing stationary boilers. SEE is used at low and moderate temperatures and it is installed with both injection as well as extraction wells that are used to inject steam into the subsurface while simultaneously extracting steam, vapors, mobile, non-aqueous phase liquid known as N naples, and groundwater. The injected steam is used to heat the subsurface to target treatment temperatures, typically the boiling point of the contaminant of concern at the site. SEE utilizes the following contaminant removal and destruction mechanisms: displacement as a N-NAPL phase and extraction with the pumped groundwater, vaporized in the steam zone, accelerated vaporization and extraction in the vapor phase through pulse pressurization and depressurization cycles, and finally dissolution, destruction, and removal with the extracted water. At the bottom of the slide, you can see an image of a SEE, which shows both upper and lower steam along with an extraction well. In this example, the steam flow and zone are governed by a low K zone at about 5 to 6 meters in depth. Also, when using this technique, it is important to remember and/or consider the monitoring and adjustments during heat up are important and expensive as well. A significant benefit of SEE is the ability to conduct pressure cycling to improve contaminant removal rates. After the target zone has been heated and the majority of the N-NAPL extracted as a liquid, pressure cycling is induced by varying the injection pressure and the applied vacuum. This process has been shown to achieve very low concentrations in the original source zone.
The next section of the presentation is the demonstration level. In this section, we will be looking at case studies for each of the thermal remediation methods. First, we will be looking at a conductive heating case study. Conductive heating was used to remove polychlorinated biphenols from a Missouri Electric Works Superfund site in Cape Girardeau, Missouri. Missouri Electric Works, Inc. operated on a 6.4-acre site from 1953 until 1992. They serviced, sold, and maintained electric motors, transformers, and transformer controls. In October of 1984, the site was inspected, and many 55-gallon drums of waste transformer oil was found. It was estimated that 28,000 gallons were released on site, which resulted in a high contamination level of 58,000 milligrams per kilogram. The contamination was found in the surface soils, subsurface soils, and drainage pathways. The PCBs were found at depths up to 10 feet, with the highest concentrations found from 0 to 4 feet deep. Thermal heaters were set up in a triangular pattern as shown in Figure 1. Heaters and vacuums were used to extract and collect the PCB vapors so they could be sent for further processing. There were 3 phases of the process. The first was where the soil temperature rose to the boiling point of water. The second was where water boiling had occurred. And the third was a superheating phase where the soil temperatures rose over 1,000 degrees Fahrenheit. The in situ thermal desorption reduced the PCB contamination in soils at the site to below the cleanup level of 2 milligrams per kilogram. The process exceeded the removal goal. It was also found that the heating process increased soil porosity from 30 to 40%, and permeability increased from 1 times 10 to the negative 3 to 30 millidarcy. This was attributed to the removal of organic matter, clay desiccation, and evaporation of in situ soil moisture. The next case study we will be evaluating is for electrical resistivity heating. The Sorrento Valley site in San Diego, California, was found to be contaminated with DNAPL. Feasibility studies were conducted with more than 1,000 groundwater samples and 300 soil samples taken. This resulted in the determination of electrical resistivity heating to be the best technology for the remediation of the site. The electricity flows between subsurface electrodes, heats the subsurface, and produces in situ steam. The electricity will heat tight soil lenses as well as the DNAPL hotspots, and the DNAPL is extracted in the vapor phase to be treated. Objectives of the remediation are to shrink and stabilize the groundwater DNAPL plume, as well as reduce the mass at the source. It was estimated that a minimum of 47,105 pounds of mass was recovered or destroyed. This resulted in 99.9% CVOC mass reduction in the soil and 99.5% CVOC mass reduction in the groundwater. Figure 2 shows the shallow groundwater results on the top and the deep groundwater results on the bottom. The last case study we will be looking at is for steam-enhanced extraction. AG Communications site, located near Chicago, Illinois, operated as a telecommunications manufacturing facility. Trichloroethene, TCE, and mineral spirits were used in the manufacturing processes and were stored in underground storage tanks. The TCE and other chlorinated solvents like cis-1,1-dichloroethene and components of the mineral spirits, which are petroleum hydrocarbons including benzene and xylene, were found in the groundwater and soil of the site. The site consisted of 3 till layers and an overlying dolomite bedrock layer. The contaminations were present mainly in the till layers, where the chlorinated solvents were present in both DNAPL and dissolved phase, and the petroleum hydrocarbons were present in both the LNAPL and dissolved phase. The contaminant concentration of TCE was greater than 45,000 micrograms per liter in the groundwater. The steam-enhanced extraction system included shallow vapor extraction wells, shallow and deep steam injection wells, vacuum-enhanced groundwater vapor extraction wells, deep groundwater extraction wells, and 2 vacuum extraction units. The objective of this system was to demonstrate that there was no on- or off-site receptors at risk from volatile organic carbons in the soil or groundwater. Most wells showed a reduction of TCE of over 90%, being reduced from about 20,000 micrograms per liter to less than 1,000 micrograms per liter. The total hydrocarbon removal for the SEE system was 33,000 pounds. About 2/3 of the contaminant mass was removed as vapor. This resulted in showing that steam-enhanced extraction improves the rate of hydrocarbon removal. The site completed remediation due to the soil under the building and the groundwater exceeding the remediation goals.
We are focusing primarily on 3 in situ thermal technologies, which are conductive heating, electrical resistance heating, and steam-based heating. All of these technologies involve raising the temperature of the subsurface to enhance the removal of NAPL components, either through viscosity reduction and increased mobility to enhance recovery by liquid pumping, or through vapor pressure increases to enhance recovery by vapor extraction. Each of these methods are applied in situ, meaning without excavating the contaminated zone. Thus, they can be used in hard-to-access locations such as between buildings, beneath buildings, in deep zones, and at places where there is established infrastructure. They are low-impact methods relative to excavation, making them well-suited for use in industrial, commercial, and residential locations, and where there are mixed uses. They are also relatively fast, meaning that the source area can be treated and removed in well less than a year if required. The degree of removal achieved may reflect the skill of designers and operators as much as inherent limitations of the technology or challenges associated with the subsurface environment. In any case, some level of post-treatment groundwater impact is expected at many DNAPL source zones, and the challenge appears to be in the balancing of the cost of treatment and the degree of groundwater quality improvement achieved. It can also be noted that in situ thermal technology performance is less hindered by the geological stratification and mass transfer resistances that limit other in situ remediation technologies. Thermoconductive heating is an in situ thermal remediation technique that relies on the use of heating elements, typically electrically powered, suspended inside steel pipes in contact with the soil. The operating temperature of the heating elements is typically between 1,000 to 1,500 degrees Fahrenheit, which is more commonly known to be 540 to 815 degrees Celsius. Conductive thermal heating functions well at a wide range of soil types as well as heterogeneous soils by heating the soils and groundwater as well as treating various types of organic contaminants. Here is a video to further explain how thermal conductive heating is used to remove contaminants from the subsurface.
Conductive heating. Electrical heater wells are installed in the contaminated subsurface. Only heat is applied to the subsurface using renewable energy. The heat spreads by thermal conduction below and above water table and is almost uniform for the entire range of soils. The technology works in geologies ranging from gravel, sand, clay, all the way to solid rock like granite to any depths. Thermal conductive heating technology is the only in situ heating technology that can reach temperatures at several hundred degrees Celsius and can thereby treat any kind of organic contaminants with low to high boiling points like gasoline, chlorinated solvents, all the way to PCB, dioxins, and even mercury. Contaminants are vaporized according to their boiling point temperature and extracted to the surface, vacuumed and treated in an above-ground treatment process. The heating process typically lasts 3 to 6 months, depending on contaminant type and concentrations. At the end, almost 100% of the contaminants are removed by electrical thermal conductive heating technology.
Electrical resistant heating remediation technologies operate by passing electrical currents through the soil between electrodes installed at the site of interest where the soil temperature is then increased. This type of remediation requires the use of electrical power, so it is very important that there are viable sources at the site in order to effectively remove the contaminants. These technologies also operate at lower temperatures than conductive heating, at approximately 80 to 110 degrees Celsius, where then the volatile chemicals are vaporized and extracted through the recovery wells. Because the heating is limited to the boiling point of water, once the water has boiled off, electrical conductivity becomes negligible. This process can be carried out in very short time frames, typically ranging somewhere from 6 to 18 months in order to meet the remediation standards set by the client. Steam-based heating techniques are most effective for heating permeable subsurface zones and perform typically well via enhanced oil recovery. This technique operates at sites with high groundwater flow because it can deliver more energy to the site. With more energy delivered, there is then more energy to overcome energy removal caused by the movement of groundwater flow. It is also important to note that fuel is required to produce the steam used where it is generated above ground and injected through wells inserted within the area of contamination. Presented below is a table that summarizes the design information for steam-based heating, resistance heating, conductive heating, and other forms of heating. Of the 121 sites tested, 117 provided data. The available treating sites involved treating areas less than 4 times 10 to the 4 feet squared, which is approximately less than 3,716 meters squared, or about 1 acre, and roughly 2/3 of those involved treatment zones operate in areas smaller than 10 to the 4 feet squared, which is less than 929 meters squared, or about 1/4 of an acre. Based upon the data below, it can be concluded that steam-based heating typically operates in target treatment zones with sizes of less than 10 to the 4 feet squared. The same can also be said about conductive heating. It had approximately 19 sites within the target treatment zone with the size of less than 10 to the 4 feet squared, and only 6 sites that fall within the size range of 10 to the 4 to 4 times 10 to the 4 feet squared. and 0 sites falling in any size greater than 4 times 10 to the 4 power feet squared. Whereas for the case of electrical resistance heating, there is about a similar number of sites within the target treatment zones of the sizes both less than 10 to the 4 feet squared and within the range of 10 to the 4 to 4 times 10 to the 4 feet squared ranges, but also having 0 sites in the target treatment zone of the size greater than 4 times 10 to the 4 feet squared. On the right-hand side of this data table, operating conditions based upon temperature ranges were tested. Of the 95 applications for which temperature data was available, 63 were operated at temperatures in the range of 80 degrees Celsius to 110 degrees Celsius in the target treatment zone. With respect to technology, most, meaning 37 of the 46, or 80% of the electrical resistant heating applications were operated within that 80 degrees Celsius to 110 degrees Celsius range. Whereas 1/3, or 7 of 21, of the steam applications were operated at temperatures less than 80 degrees Celsius, and about half of the conductive heating applications were operated at temperatures greater than 110 degrees Celsius. The takeaway from this part of the data table concludes that conductive heating technologies operate at much greater temperatures than do the steam-based heating techniques and the resistance heating techniques, which then operate typically in ranges of 80 degrees to 110 degrees Celsius.
There are multiple factors that influence the cost of thermal remediation. The site characteristics is the primary factor influencing the cost. Those parameters include the soil characteristics, which involves the permeability and the soil type, the contaminant depth, which is the vertical depth to the contaminant zone, and then the contaminant volume is also a major influence because that determines essentially the amount of contaminants that need to be removed, the contaminant type, as well as the physical site geography. For example, if the site is located on the side of a mountain, it is harder to access than on a flat plane, which the site characteristics in turn determines the number of wells required. More wells means the cost is going to be increased. The equipment and process efficiency is also a factor. This involves the efficiency of the equipment and the process itself, not the overall remediation efficiency. Thermal remediation efficiency tends to be quite high, but if your equipment only operates at, say, 50% efficiency, it's going to take longer than an equipment and process combination that works at 85% efficiency. So therefore, a longer on-site time will increase the cost of the remediation. That leads into the treatment rate. If you're able to treat the contaminant at a faster rate than a different process, then the cost will be lower because it doesn't take as long to treat the contaminants. This also depends on specific site characteristics such as permeability, the depth to the contaminant zone, as well as the contaminant volume and type. On this slide, we have 4 different costing scenarios based on differences between site parameters as well as soil characteristics. All of the scenarios are based on removing volatile organic compounds from the soil by thermal remediation methods. You'll see the first 2 columns, scenario A and scenario B, are based on a small site of 5,000 square feet, while scenario C and scenario D are a large site based on 15,000 square feet. Both the depth of the contaminant area as well as the thickness of the contaminant zone are equal in all scenarios to make an equal comparison. This is further divided by a difficult as well as an easy remediation based on the soil type. For an easy site remediation, we have silt and silty clay that has a permeability of 0.1. And a difficult situation involves a soil type of sand and gravelly sand with a permeability of 5. If you notice, the permeability of the easier site is lower, and this permeability of the difficult site is higher. That is because a lower permeability tends to be cheaper and easier to remediate because it requires less gas flow. Furthermore, we are not going to pay a lot of attention to exact dollar amounts because these amounts are going to change for every remediation project, as well as any company who bids the project or does a cost analysis for it. What we will focus here on is the total cost differences between the small site and the large site, as well as the cost per cubic yard in both of these scenarios. You'll see that for a small site, an easy small site will come in roughly at $282,000, while a small difficult site goes up to $341,000. These are both quite a bit lower than a large site. An easy large site will come in at roughly $485,000, and a large difficult site is roughly $626,000. So large sites tend to be overall significantly more expensive than a small site, but when you look at the cost per cubic yard, you'll find that the cost per cubic yard of a small site tends to be significantly greater than the cost per cubic yard of a large site. A small easy site tends to be roughly $51 a yard based on removing 5,550 cubic yards of contaminants, or processing 5,550 yards of soil. While the large easy site only cost $29 per cubic yard, and that is processing 16,650 cubic yards of soil. So what to note here is, while a large site is more expensive overall, you can consider it almost as buying in bulk. All of your individual components, your cost per cubic yard, is overall cheaper than a small site. The availability of thermal remediation largely depends on your specific site characteristics, such as the physical geography, the soil characteristics, as well as the contaminant characteristics. And if your remediation project doesn't involve the exact site characteristics that thermal remediation requires, this will not be an option that's available to you. Therefore, your availability is quite low. On the plus side, there are numerous companies who offer thermal remediation and in various thermal remediation methods. Those companies include, a few of those companies, not all, include TerraTherm Thermal Remediation, Hamer's Technology, as well as Insiu Oxidative Technologies. Those are just to name a few. And it also depends on where the contaminant site is located, depending on which company is closer. A company that is closer may offer a lower cost than a company that's all the way across the country or on the other side of the world, naturally. So the availability of thermal remediation vastly depends on the site location, as well as the geography and other characteristics of the soil and contaminants.